Welcome. Today, we embark on a journey to uncover the secrets behind training neural language models. These powerful tools are at the heart of modern artificial intelligence, enabling machines to understand and generate human language. But how do they actually learn? In this video, we'll break down the core concepts, explore the training process, and reveal the techniques that make these models so effective. Whether you're new to AI or looking to deepen your understanding, you'll find valuable insights as we move from the basics to advanced strategies. Let's get started by understanding what neural language models are and why they matter. Neural language models are a type of artificial intelligence designed to process and generate human language. They use neural networks which are inspired by the human brain to learn patterns in text data. By analyzing vast amounts of language, these models can predict the next word in a sentence, translate languages, summarize articles, and even write stories. Their ability to understand context and meaning has revolutionized natural language processing, making applications like chatbots and virtual assistants possible. Next, let's look at the basic structure of these models and how they function. The heart of every neural language model are several key components. First, there's the input layer, which takes in text data and converts it into a format the model can understand. Next, hidden layers process this information, identifying patterns and relationships between words. Finally, the output layer generates predictions or responses. These layers are connected by millions of parameters, which the model adjusts during training to improve its accuracy. Understanding these components is crucial for grasping how language models learn and perform complex tasks. Training a neural language model requires massive amounts of text data. This data can come from books, articles, websites, and conversations. The more diverse and extensive the dataset, the better the model can learn the nuances of language. During training, the model reads through this data, learning grammar, vocabulary, and context. High-quality data is essential, as it directly impacts the model's ability to generate accurate and meaningful language. Let's explore how this data is prepared and used in the training process. Before training begins, the raw text data must be cleaned and organized. This process, known as data preprocessing, involves removing errors, duplicates, and irrelevant content. The text is then tokenized, meaning it's broken down into smaller units like words or subwords. This step ensures the model can efficiently process and learn from the data. Proper preprocessing not only improves training efficiency, but also helps the model avoid learning incorrect patterns. Now let's see how the model uses this processed data to start learning. Tokenization is a fundamental step in preparing text for neural language models. It involves splitting sentences into smaller pieces, such as words or even characters. These tokens are then mapped to numerical values, allowing the model to process them mathematically. Tokenization helps the model understand the structure of language and manage large vocabularies efficiently. By breaking down text into manageable parts, tokenization lays the groundwork for effective learning and prediction. Once text is tokenized, the next step is to convert these tokens into word embeddings. Word embeddings are numerical representations of words that capture their meanings and relationships. By placing similar words close together in a mathematical space, embeddings help the model understand context and semantics. This technique allows neural language models to recognize synonyms, analogies, and subtle differences in meaning, making their predictions more accurate and natural. Architecture of a neural language model determines how it processes and learns from data. Common architectures include recurrent neural networks (RNNs), long short-term memory networks (LSTMs), and transformers. Each has its strengths. RNNs handle sequences, LSTMs remember long-term dependencies, and transformers excel at parallel processing. Choosing the right architecture is key to building an effective language model. Let's dive deeper into how these architectures work. Current neural networks, or RNNs, are designed to process sequences of data, such as sentences or paragraphs. They use loops to remember information from previous steps, making them well-suited for language tasks. However, RNNs can struggle with long-term dependencies where important information is far apart in the text. Despite this limitation, RNNs laid the foundation for more advanced architectures and are still used in many applications today. Long short-term memory networks, or LSTMs, were developed to address the limitations of RNNs. LSTMs use special gates to control the flow of information, allowing them to remember important details over longer sequences. This makes them highly effective for tasks like language modeling, translation, and speech recognition. LSTMs have played a crucial role in advancing the capabilities of neural language models. Transformers represent a major breakthrough in neural language modeling. Unlike RNNs and LSTMs, transformers use attention mechanisms to process all parts of a sequence simultaneously. This allows them to capture complex relationships and context more efficiently. Transformers have become the backbone of state-of-the-art models like BERT and GPT, powering many of today's most advanced AI applications. Training a neural language model involves feeding it large amounts of processed text and adjusting its parameters to minimize errors. The model makes predictions, compares them to the correct answers, and updates its internal weights using algorithms like backpropagation. This iterative process continues until the model achieves a desired level of accuracy. The training process is computationally intensive, often requiring powerful hardware and specialized software. Key part of training is the loss function, which measures how far the model's predictions are from the correct answers. Common loss functions for language models include cross-entropy loss, which penalizes incorrect predictions more heavily. By minimizing the loss function, the model learns to make better predictions over time. Understanding loss functions is essential for optimizing model performance. Optimization algorithms are used to update the model's parameters during training. Popular algorithms include stochastic gradient descent (SGD) and ADAM. These methods adjust the model's weights in small steps, gradually improving its accuracy. Choosing the right optimizer can significantly affect training speed and final performance. Let's look at how these algorithms work in practice. Instead of training on the entire dataset at once, neural language models often use batch training. This means the data is divided into smaller groups or batches which are processed one at a time. Batch training helps manage memory usage and can speed up the training process. It also introduces some randomness which can help the model generalize better to new data. Training a model involves multiple passes through the dataset known as epochs. Each epoch allows the model to learn from the data and refine its predictions. Within each epoch, the model processes batches of data in iterations. The number of epochs and iterations is carefully chosen to balance learning and avoid overfitting, where the model memorizes the training data instead of generalizing. Prevent overfitting, regularization techniques are used during training. Methods like dropout randomly deactivate parts of the network, forcing the model to learn more robust features. Other techniques include weight decay and early stopping. Regularization helps ensure the model performs well on new, unseen data, making it more reliable in real-world applications. After training, it's important to evaluate the model's performance using specific metrics. Common metrics for language models include accuracy, perplexity, and BLEU score for translation tasks. These metrics help determine how well the model understands and generates language. Regular evaluation ensures the model meets the desired standards before deployment. Once a base model is trained, it can be fine-tuned for specific tasks or domains. Fine-tuning involves additional training on a smaller, specialized dataset. This process allows the model to adapt to unique language styles, technical jargon, or specific industries. Fine-tuning is a powerful way to customize language models for real-world applications. Transfer learning is a technique where a pre-trained model is adapted to a new task. Instead of training from scratch, the model leverages knowledge gained from previous training. This approach saves time and resources and often leads to better performance, especially when data is limited. Transfer learning has become a standard practice in modern language modeling. Hyperparameters are settings that control the training process, such as learning rate, batch size, and number of layers. Tuning these parameters can significantly impact model performance. Researchers often experiment with different values to find the optimal configuration. Hyperparameter tuning is both an art and a science, requiring careful testing and analysis. Training large neural language models demands significant computational resources. Powerful GPUs, TPUs, and distributed computing systems are often used to handle the massive calculations involved. Efficient hardware and infrastructure can dramatically reduce training time and enable the development of more complex models. Let's see how technology supports large-scale training. Distributed training involves splitting the training process across multiple machines or devices. This approach allows for faster training and the ability to handle larger datasets. By coordinating updates between devices, distributed training ensures the model learns efficiently and scales to meet growing demands. Training neural language models is not without challenges. Issues like data quality, computational cost, and model bias can impact results. Addressing these challenges requires careful planning, robust data pipelines, and ongoing monitoring. Despite the obstacles, advances in research and technology continue to push the boundaries of what's possible. Model bias occurs when a language model learns and reproduces unfair or prejudiced patterns from its training data. This can lead to problematic outputs and reinforce stereotypes. Addressing bias involves careful data selection, regular evaluation, and the use of fairness metrics. Ongoing research aims to make language models more equitable and responsible. Ethics play a crucial role in training and deploying neural language models. Developers must consider privacy, consent, and the potential impact of AI-generated content. Transparent practices and clear guidelines help ensure that language models are used responsibly and for the benefit of all users. Neural language models power a wide range of applications, from virtual assistants and chatbots to translation services and content generation. Their ability to understand and generate human language has transformed industries like customer service, healthcare, and education. As these models continue to improve, their impact will only grow. Virtual assistants like Siri, Alexa, and Google Assistant rely on neural language models to understand and respond to user queries. These models enable assistants to interpret natural language, provide relevant information, and perform tasks like setting reminders or sending messages. The seamless interaction between humans and machines is made possible by advanced language modeling. Machine translation services such as Google Translate use neural language models to convert text between languages. These models analyze context, grammar, and meaning to produce accurate translations. The result is faster, more reliable communication across language barriers, supporting global collaboration and understanding. Neural language models are increasingly used to generate content, from news articles and reports to creative writing and marketing copy. By understanding context and style, these models can produce human-like text that meets specific requirements. Content generation tools are transforming the way information is created and shared. Language models can summarize long documents and answer questions based on provided text. These capabilities are valuable in research, education, and customer support, where quick access to relevant information is essential. Summarization and question answering demonstrate the practical power of neural language models. Speech recognition systems convert spoken language into text using neural language models. These systems are used in voice assistants, transcription services, and accessibility tools. By accurately interpreting speech, language models make technology more accessible and user-friendly for everyone. Personalization is another key application of neural language models. By analyzing user preferences and behavior, these models can tailor recommendations, content, and interactions to individual needs. Personalization enhances user experience and engagement across digital platforms. Neural language models can be updated and improved over time through continuous learning. By incorporating new data and feedback, models stay current and adapt to changing language trends. Continuous learning ensures that language models remain effective and relevant in a dynamic world. Many neural language models are developed and shared as open-source projects. This collaborative approach accelerates innovation and allows researchers and developers worldwide to contribute improvements. Open-source communities play a vital role in advancing the field of language modeling. Some of the most well-known neural language models include BERT, GPT, and T5. Each model has unique strengths and is used for different applications. BERT excels at understanding context, GPT generates coherent text, and T5 is versatile for multiple tasks. These models have set new standards in natural language processing. Recent trends in language modeling involve scaling up models with more parameters and larger datasets. Bigger models can capture more complex patterns and deliver better performance, but they also require more resources to train and deploy. Balancing scale and efficiency is a key challenge for researchers. As models grow larger, energy efficiency becomes increasingly important. Researchers are developing new techniques to reduce the energy consumption of training and running neural language models. Efficient algorithms and hardware help make AI more sustainable and accessible. Model compression techniques aim to reduce the size and complexity of neural language models without sacrificing performance. Methods like pruning, quantization, and knowledge distillation make models faster and more efficient, enabling deployment on devices with limited resources. Deploying neural language models involves integrating them into real-world applications. Strategies include cloud-based deployment for scalability and edge deployment for low-latency responses. Choosing the right deployment method depends on the application's requirements and available resources. After deployment, language models require ongoing monitoring and maintenance. This includes tracking performance, updating data, and addressing any issues that arise. Regular maintenance ensures the model continues to deliver accurate and reliable results over time. Future of neural language models is bright, with ongoing research focused on improving efficiency, reducing bias, and expanding capabilities. Emerging trends include multilingual models, zero-shot learning, and more human-like understanding. As technology advances, language models will become even more powerful and versatile. Multilingual neural language models are designed to understand and generate text in multiple languages. These models enable cross-lingual applications and support global communication. By training on diverse datasets, multilingual models break down language barriers and make AI accessible to more people worldwide. Zero-shot and few-shot learning allow language models to perform new tasks with little or no additional training. By leveraging prior knowledge, these models can generalize to unfamiliar situations. This capability opens up exciting possibilities for rapid adaptation and flexible AI solutions. We've explored the secrets of training neural language models, from data preparation and architecture to deployment and future trends. These models are transforming the way we interact with technology, making machines more capable of understanding and generating human language. As research continues, we can expect even greater advances in natural language processing. Thank you for joining this journey into the world of neural language model. Stay curious and keep exploring the possibilities of AI.